Welcome to Lyons Township High School, AP Physics 1. Today we got an example involving a ball rolling down a ramp. Ball starting from rest. Given the moment of inertia of a solid ball is 2/5 mr squared. And it's starting from rest, and we're going to assume that there is enough friction so that it just simply rolls down the hill, doesn't slip at all. Okay? And we're going to figure out two things about it. We're going to figure out what's its final velocity when it travels a distance x down the hill, and what's the acceleration of the ball as it goes down the hill. Now, I will make a note here. If this were a cart, okay, if this were a cart, the acceleration, or the final velocity of a cart would be root 2 gx sine of theta. Okay, so if you were if it was just a frictionless cart rolling down the hill, the velocity would be that, and the acceleration would simply be g sine of theta. So that would be, for Physics 1, that would be way back in Chapter 4. We would say, hey, draw an FBD of the cart, assuming there's no friction or low friction, find the acceleration of the acceleration of the cart down the hill and the final velocity of the cart down the hill, and these would be the answers you'd get. Okay. Now, how does that compare to the ball? Okay. So will the ball go faster than the cart, or slower than the cart, or the same as the cart? Will have a greater or less or equal acceleration, and therefore greater or less or equal velocity. Okay. Well, we're going to calculate that, and then in Physics 1 we do race them, by the way, so we can figure that out before we do the calculations. But anyway, so we're going to do the same process. Okay. For the ball, you can either find the final velocity first, or you can find the acceleration. And it turns out that there's at least 4 ways that I can think of to solve this problem. Okay, I'm going to kind of lead you through what I think is the easiest of those 4 ways, but there's lots of ways you can solve this problem. Okay, so I'm going to find the final velocity first. And generally speaking, when you have an object traveling from point A to point B, usually the easiest way to find information about it is to use conservation of energy. So for this problem, we're going to use conservation of energy as the ball travels from the top of the incline to the bottom. Okay, so we're going to write our conservation of energy equation down. We've got potential energy at the beginning plus kinetic energy at the beginning plus the work done by any non-conservative forces as it travels from the point 1 to point 2 is going to equal potential energy final plus kinetic energy final. Now, by the way, your teacher may use different symbols for these, but this is potential energy and that's just kinetic energy. Now, mind you, kinetic energy, there are at least 2 types that we can talk about for now. If the ball is moving, it's got translational kinetic energy, and if it's spinning, it's got rotational kinetic energy. Well, hopefully you'll see as the ball is going down the hill, it's doing both. It's moving translationally and it's spinning. So over here, there's going to actually be 2 terms there. One for the translational motion, the center of mass moving, and one for the spinning. Okay, that's the rotational kinetic energy. So several of these are 0. So for instance, at the bottom of the hill, we'll call this 0 height. So at the bottom of the hill, that's 0. Okay, it starts from rest, so Ke naught 0. Now there are non-conservative forces acting on the ball. Matter of fact, there's 2 non-conservative forces acting on the ball. Just out of note, there's 3 total forces acting on the ball. There's gravity. Well, that's a conservative force, so that's going to go in here, so you don't worry about that. There is the normal force of the ramp pushing up this way on the ball. But that normal force doesn't do any work because that normal force is perpendicular to the motion. So the normal force doesn't do any work. The other force and this is a little trickier, the other force that's acting on this ball is friction. If there was no friction, the ball would simply do this down the hill, which is slide. Well, we want it to roll. So it turns out that friction acts this way on the ball. Okay? So there is the non-conservative force of static friction, by the way. It's static because you want the ball to roll, not slide. So if the ball is rolling, you're talking about static friction. In other words, this point on the ball is not moving relative to the ramp. Which leads me to my last point. does that friction do any work? Okay, well, no. Since this point, when the ball rolls, that point, no matter what point in the motion I pick, that point on the ball is not moving. So since that point on the ball is not moving, friction's not doing any work. Okay, there's no distance through which friction acts. Now, friction does do something energy-wise here, and I'll kind of explain that in a minute, but overall, this term is zero, which kind of makes it nice, okay? At the beginning, we have potential energy. It's gravitational potential energy, so that's mgh. At the end, as I mentioned before, we have two kinds of kinetic energy. We have translational kinetic energy, the center of mass moving. Well, that's 1/2 mv squared. But the ball is also spinning about the center of mass. You have rotational energy, which is 1/2 I omega squared. So we're going to make some substitutions in here. For instance, what's the height? Well, I gave you x. We need the height. Well, this is a right triangle. X is the hypotenuse. We want the opposite leg. The opposite leg would be x sine of theta. So here, this turns into mgx sine of theta. That's just 1/2 mv squared plus 1/2. For the ball, we're given the moment of inertia of the ball. It's 2/5 mr squared. And then what's omega? Okay. Well, v equals r omega. So omega is just v over r. Now, that's squared, so I got to square both the v and the r. So this becomes a v squared over r squared. Now, once you've got that, it turns out you can do a lot of canceling here. So, for instance, you'll notice there's an m in all three terms. So the m is gone. Okay. Over here, that r squared and that r squared cancel. And even a little more, this 2 and this 2 cancel. All right. So then you get a pretty easy equation then. You got gx sine of theta equals 1/2 v squared plus 1/5 v squared. Okay. What's 1/2 plus 1/5? Well, that's 5/10 and 2/10. That's 7/10. So you got gx sine theta is 7/10 v squared. And if you get v by itself, you got v is 10 gx sine of theta over 7. That's all in the square root. So that is your final velocity of the ball at the bottom of the ramp. Now, a couple things I'll mention about that answer. Friction did something. Okay? It turns out, and this is kind of one way to think of it, friction takes some of this potential energy and turns it into rotational kinetic energy. If there is no friction, you're just going to have that. Okay? Because there's friction, we get some of this. So friction, it does move energy around in this case, but it kind of moves it from, it robs it, you can kind of think of it this way, robs it from translational kinetic energy and gives it to rotational kinetic energy. So that's one thing that friction does. Something else you'll notice, the final velocity of the ball compared to the final velocity of a cart. The final velocity of the ball is less. It's, instead of 2 gx sine theta, it's 10 over 7. That's less than 2. It's whatever, 1.3 roughly. Gx sine theta is square root. So friction does make the acceleration of the ball less than that of a cart. Friction is part of that net force equals ma equation. So friction, it reduces the acceleration of the ball. Okay, so it does do some things. It doesn't take any energy out of your system. Okay, that's a good thing. All right, so you got the final velocity of the ball. Now to find the acceleration of the ball, once you have this, the easy way is just to use kinematics. I would personally use v final squared equals v naught squared plus 2a delta x. We've got v final, it's that. If I square it, the square root goes away, so you got 10 gx sine theta over 7 equals, that's 0, 2. We're trying to find a, and delta x is simply x in our problem. Some stuff, a couple things cancel. The x is gone. The acceleration doesn't depend on how long the ramp is. The acceleration just depends on the angle of the ramp. And then this 2, and that becomes a 5. Okay? And you get A. So A is 5g sine theta all over 7. Now, I'll mention the same thing again about comparing the ball to the cart. The acceleration of the ball is 5/7 g sine theta. The acceleration of the cart is g sine theta. So the acceleration of the ball is a little bit less. And that's, again, partly because friction is trying to slow the ball down. It's resisting the motion of the ball. Okay? So I hope that example was helpful, and thank you very much.